Merry Christmas, everybody! Apache Mesos is a distributed systems kernel that abstracts and manages compute resources across a cluster of machines, enabling efficient resource sharing among multiple frameworks and applications. It provides a unified resource management system for deploying and running distributed applications, making it easier to build fault-tolerant and scalable systems. Mesos is widely used for big data processing, container orchestration, and general purpose resource management in modern data centers. For more tech interview materials, please visit our website bowz8.com. Core components include 1. Master node. Coordinates resource allocation across the cluster and communicates with frameworks. 2. Agent nodes slaves. Run on individual machines to report available resources and execute tasks assigned by frameworks. 3. Frameworks. Applications that request resources from Mesos to perform specific tasks. Examples include Apache Spark and Marathon. 4. Schedulers. A component within a framework responsible for requesting resources and launching tasks. 5. Executors. Manage the execution of tasks on agent nodes, as directed by the framework scheduler. 6. Resource offers. Mesos uses a resource offer model where the master presents available resources to frameworks, and frameworks decide how to utilize them. What happens under the hood? 1. Resource discovery. Agent nodes report their available resources, CPU, memory, disk, etc., to the master node. 2. Resource offers. The master sends resource offers to frameworks based on available resources and predefined constraints. 3. Task scheduling. Frameworks decide which tasks to run using the offered resources and submit those tasks back to Mesos. 4. Task execution. The executor on an agent node runs the tasks assigned by the framework and reports task status back to the master. 5. Fault tolerance. If a node fails, tasks running on that node are rescheduled on other available nodes. Example use cases are big data processing. Running distributed data processing frameworks like Apache Spark and Apache Hadoop. Container orchestration. Managing containerized applications using frameworks like Marathon or Kubernetes. General resource management. Sharing cluster resources among multiple applications and services efficiently. Batch and stream processing. Handling compute-heavy workloads in batch or real-time scenarios. Advantages include 1. Scalability. Designed to scale to tens of thousands of nodes in a cluster. 2. Resource efficiency. Enables multiple frameworks to share the same cluster, optimizing resource utilization. 3. Flexibility. Supports a wide range of workloads, including big data, container orchestration, and custom applications. 4. Fault tolerance. Resilient to node and task failures with automatic rescheduling of tasks. 5. Open frameworks. Supports integration with existing and custom frameworks. Limitations include 1. Complexity. Setting up and managing a Mesos cluster requires significant expertise. 2. Steep learning curve. Developers and operators need to understand Mesos internals and frameworks. 3. Competition. Other resource managers like Kubernetes have gained significant traction, reducing the demand for Mesos. 4. Limited native features. Mesos relies on external frameworks for specific functionalities, requiring additional components for orchestration. Thanks for watching. I wish you a Merry Christmas and Happy New Year. For more tech interview materials, please visit bowz8.com. Merry Christmas, everybody! Apache Cassandra is a highly scalable, distributed NoSQL database designed to handle large amounts of data across many commodity servers with no single point of failure. It excels in scenarios requiring high availability, horizontal scalability, and fault tolerance, making it popular for big data and real-time analytics applications. For more tech interview materials, please visit our website bowz8.com. Core components include 1. Cluster. A collection of nodes working together to form a distributed database. 2. Node. The basic unit of Cassandra, representing an individual machine in a cluster. 3. Data center. a group of related nodes, often representing physical or logical separation. 4. Keyspace, a namespace in Cassandra, analogous to a database in relational systems, defining replication strategy and schema. 5. Tables, schema-based structures that store data, similar to tables in relational databases. 6. Partition and tokens. Data is divided into partitions using partition keys and distributed across nodes via consistent hashing. 7. Replication. Data is replicated across nodes for fault tolerance. The replication factor determines the number of copies. 8. Commit log, a durable record of all write operations, ensuring data persistence. 9. Memtable and SSDables. Data is first written to an in-memory structure, memtable, and later flushed to disk as immutable SSDables. 10. Cassandra Query Language, (SQL), the primary interface for interacting with Cassandra, similar to SQL. What happens under the hood? 1. Write path. Data is written to the commit log for durability and then stored in the memtable. Periodically, the memtable is flushed to disk as SSDables, which are immutable and compacted over time. 2. Read path. Queries first check the memtable, then SSDables, and finally the Bloom filter and indexes to locate data efficiently. 3. Replication. Data is distributed across nodes based on the partition key and replicated as per the configured replication strategy. 4. Consistency levels. Users can tune consistency levels, e.g., 1, quorum, all, to balance data consistency, availability, and latency. 5. Failure handling. If a node fails, other nodes with replicated data handle requests, ensuring continuous operation. Example use cases are IT applications, handling large volumes of time series data from connected devices, real-time analytics, powering recommendation engines, fraud detection, and personalized user experiences, social media platforms, managing user profiles, messages, and activity feeds, e-commerce, supporting product catalogs, inventory management, and user sessions. Advantages include 1. High availability, designed for zero downtime with no single point of failure. 2. Horizontal scalability, easily scale out by adding nodes without downtime. 3. Fast writes, optimized for write-heavy workloads. 4. Tunable consistency, flexibility to configure consistency levels based on use cases. 5. Fault tolerance. Data replication across nodes ensures durability and availability. Limitations include 1. Complex query language, limited relational capabilities, and lack of join operations. 2. Operational overhead, requires expertise to manage cluster operations and optimize performance. 3. Storage overhead, high replication factor increases storage requirements. 4. Eventual consistency, trade-offs in strong consistency for availability in some configurations. Thanks for watching. I wish you a Merry Christmas and Happy New Year. For more tech interview materials, please visit bowsy8.com. Merry Christmas, everybody! Apache Thrift is an open-source framework designed to enable scalable cross-language communication for microservices and distributed systems. It provides a comprehensive solution for defining data types and service interfaces and generating client and server code for various programming languages. For more tech interview materials, please visit our website bowsy8.com. Core components include 1. Interface Definition Language, IDL, a language-agnostic format used to define data structures and service interfaces. 2. Compiler, converts IDL definitions into code stubs for supported languages, e.g., Java, Python, C++, Go. 3. Protocols, define the serialization format for communication, e.g., binary, compact, JSON. 4. Transports, handle data transfer mechanisms such as in-memory buffers, sockets, or HTTP. 5. Processors, the server-side component that processes incoming requests and invokes the appropriate service methods. 6. Servers, hosts the Thrift service, managing client connections and request handling. What happens under the hood? 1. Define interfaces and data structures. Developers use Thrift IDL to define service interfaces and data structures in a language-neutral way. 2. Code generation. The Thrift compiler generates client and server stubs in target programming languages. 3. Serialization and deserialization. Data is serialized using the selected protocol for transmission and deserialized upon receipt. 4. Transport mechanism. Transports manage data transmission between clients and servers, ensuring reliability and efficiency. 5. Request processing. The server-side processor decodes requests, invokes service methods, and sends responses back. Example use cases are microservices communication, seamless interaction between services written in different languages, data serialization, efficient data exchange for applications like big data pipelines, cross-platform API development, simplifies API development for applications targeting multiple languages, high-performance RPC systems, supports low latency and high-throughput remote procedure calls. Advantages include 1. Cross-language support. Generates code for a wide range of programming languages. 2. Performance. Optimized serialization protocols and transport layers ensure high throughput. 3. Flexibility. Provides multiple protocols and transport options to suit diverse use cases. 4. Ease of use. Simplifies the development of cross-language systems with auto-generated code. 5. Scalability. Designed for large-scale, distributed environments. Limitations include 1. Steep learning curve. Requires familiarity with IDL and generated code integration. 2. Complexity. Advanced features like custom transports or protocols may be challenging to implement. 3. Limited extensibility. Modifying or extending generated code can be cumbersome. 4. Debugging overhead. Troubleshooting issues across multiple languages may require additional effort. Thanks for watching. I wish you a Merry Christmas and Happy New Year. For more tech interview materials, please visit bowsy8.com. Merry Christmas, everybody! Apache Iceberg is an open-source, high-performance table format for large-scale data lakes. It addresses challenges in managing, querying, and evolving datasets over time by introducing features like schema evolution, time travel, and ACID compliance. For more tech interview materials, please visit our website bowsy8.com. Core components include 1. Table format. Defines a metadata-driven approach to store and manage large datasets in file-based systems. 2. Metadata layers. Snapshot metadata tracks the current state of the table, enabling time travel and rollback. Manifest files point to data files and provide granular details about data partitions. 3. Partitioning. Supports hidden partitioning to optimize queries without exposing partition structures to users. 4. APIs. Provides APIs for integration with distributed engines like Spark, Flink, Presto, and Hive. What happens under the hood? 1. Table abstraction. Data is organized into tables consisting of data files, manifest files, and snapshot metadata. Each table is independent and self-descriptive. 2. Data and metadata management. Data files store the actual records. Metadata management tracks changes across snapshots, ensuring consistency. 3. Optimized query execution. Engines leverage metadata to perform pruning and read only relevant files, improving performance. 4. Schema evolution. Allows users to add, remove, or modify columns without breaking older data or applications. 5. Time travel and rollbacks. Snapshots enable users to query previous states of the dataset or roll back to a specific version. Example use cases are data lakes. Manages large-scale datasets stored in systems like AWS S3, HDFS, or Azure Data Lake. Batch and streaming. Suitable for both batch processing, e.g., ETL jobs, and streaming data, e.g., real-time pipelines. Analytics and BI. Supports queries for analytics tools by enabling efficient partition pruning and consistent schema management. Compliance. Facilitates audits and historical data tracking with time travel capabilities. Advantages include 1. ACID transactions. Guarantees data consistency in write and read operations. 2. Time travel. Enables querying past states of the data. 3. Scalable and efficient. Optimized for large-scale datasets, reducing query latency. 4. Multi-engine compatibility. Integrates with major processing engines like Spark, Flink, and Trino. 5. Schema evolution. Simplifies dataset evolution without requiring rewrites. Limitations include 1. Complexity. Requires a learning curve to set up and maintain. 2. Performance overhead. Metadata management can introduce overhead in very high throughput systems. 3. Dependency management. Relies on distributed query engines, which may complicate deployment in heterogeneous environments. Thanks for watching. I wish you a Merry Christmas and Happy New Year. For more tech interview materials, please visit bowsy8.com. Merry Christmas, everybody. Apache Mahout is an open-source library designed for creating scalable machine learning applications. It focuses on distributed and efficient implementations of algorithms for classification, clustering, collaborative filtering, and dimensionality reduction. Mahout integrates well with big data ecosystems like Hadoop and Spark. For more tech interview materials, please visit our website bowsy8.com. Core components include 1. Core algorithms. Includes pre-built algorithms for machine learning tasks such as clustering, e.g., k-means, classification, e.g., logistic regression, and collaborative filtering. 2. Mahout Math Library. A robust linear algebra library supporting distributed and in-memory computations. 3. DSL, domain-specific language. A high-level, expressive syntax for building algorithms in Scala and other JVM languages. 4. Integration with distributed systems. Operates on Hadoop MapReduce and Spark for distributed data processing. What happens under the hood? 1. Algorithmic operations. Supports both distributed, Hadoop, Spark, and single-node in-memory machine learning. 2. Distributed processing. Uses Hadoop MapReduce or Spark to distribute workloads across multiple nodes for scalability. 3. Pipeline creation. Users create pipelines with its DSL, integrating algorithms and custom transformations. 4. Mathematical foundation. Performs linear algebraic computations efficiently, crucial for high-performance ML tasks. Example use cases are collaborative filtering. Building recommendation systems for e-commerce platforms or media streaming services. Clustering. Segmenting customer datasets for targeted marketing or pattern discovery. Classification. Predictive analytics, such as fraud detection or churn prediction. Dimensionality reduction. Pre-processing large datasets to remove redundancy and reduce computational overhead. Advantages include 1. Scalability. Handles large datasets efficiently by leveraging distributed processing. 2. Pre-built algorithms. Saves development time with readily available implementations. 3. Extensibility. Provides a flexible DSL for custom algorithm development. 4. Integration. Works seamlessly with Hadoop and Spark for big data machine learning. Limitations include 1. Limited focus. Primarily supports batch processing machine learning, lacks advanced support for deep learning. 2. Learning curve. The DSL and mathematical abstractions require prior knowledge of distributed computing and ML. 3. Ecosystem overlap. Competes with newer ML frameworks like TensorFlow and PyTorch. 4. Reduced popularity. Over time, Mahout's adoption has decreased as modern frameworks gain traction. Thanks for watching. I wish you a Merry Christmas and Happy New Year. For more tech interview materials, please visit bowsy8.com.